Okay, here is our review for the work energy test, and we're just going to go through one question at a time, maybe skipping some easy ones, but generally go through each one and give you a hint on how to solve it. For the first question, we're considering two pendulums, one that's pulled back at 45 degrees, the other one that's pulled back so that it's height L over 2, where L is the length of the pendulum, a height L over 2 above the lowest point. And the question is, which one has more potential energy? And so that's going to depend on which one has more height above the lowest spot. The trouble, though, with this problem is, in the one case you've got angles, in the other case you've got the height directly given to you. And to compare them, we either need to know the angle on this one or the height on that one. So let's try, it doesn't matter which one we convert into angle or height, but let's maybe start with this one. So we'll take a look at, we're looking for the height, and we can figure that out because we know that this full length right here is L. And so that means there are two sections that are both L over 2 high. And if we look at this triangle right here, we can solve for the angle, because this angle right here, we can say that the cosine of that angle is equal to adjacent over hypotenuse. Adjacent is L over 2. Hypotenuse is L. The L's cancel, and we just have 1/2 over 1, or just 1/2. And then we inverse cosine both sides, and we can figure out this angle and compare it with the 45. The other way to go would be to try to figure out how high the height is over here, and this is actually how you have to work on question number 2, which we'll talk about in a second. So how do we figure out how big this height is right here? Well, we need to figure out how big this is first. The full distance, of course, is going to be the length of the pendulum from top to bottom. And that's the length of the pendulum there. So if we've got a 45-degree angle and we're trying to find out x, it would be true that cosine of 45 in this picture, cos 45, equals x over L. And we can pick a pretend distance for L, any number we want here, just because we're just trying to figure out how much height we have as a fraction of L. And so let's just pick an L of 1. Let's just say that this happens to be 1 meter. Okay, so that means cos 45 equals x over 1, or just x. And so if we solve for x, cos 45 is equal to 0.707. So if this whole distance is 1, the full length of the pendulum, and x equals 0.707, h has to equal, therefore, h has to equal the rest of it. So that would, what would that be? 0.293. Okay. And then you can compare this h, 293, versus this h over here, which is a half. And a half is obviously much bigger than 0.293. So on question number 2, you have to compare a pendulum that's been pulled back 20 degrees versus one that has been pulled back only 10 degrees, and compare how much potential energy each has gained. 10 degrees on this one. And you're going to go through the same procedure above. Pick a number for the length. We can just use 1 meter for the length of the pendulum. and then you can calculate this distance here, and what's left over is the height that you've gone up, and that's what you're after. So you're going to compare that height, and the same thing with this other guy here. You'll figure out his height, that height right there. And then if you can compare those two heights, you can compare the potential energies, the MGHs of each. Okay? So you need to, on question 2, you need to get the heights in order to compare how much potential energy each has. All right, let's move on to question number 3. On question number 3, we are given a spring that has a K value that we are that we're trying to solve for. So the K is unknown, but we do know that it is stretched 10 centimeters. So that means that 10 centimeters is our x distance, our extension. And we know that the stored energy, U, the stored energy, is 800 joules. But we know that the stored energy is equal to 1/2 kx squared. And x is 10 centimeters, which we have to turn into meters, 100 centimeters in a meter. So if we put this value in for x, the only thing that we wouldn't know in this equation, the only thing we wouldn't know would be the k. So 0.1 goes in for x, and then you solve for your k. That's question, I guess that was question 6. We don't have a 3, 4, and 5. Okay. On question 7, we've got the same spring, but now we know the k, check. And we're now going to stretch it 16. We're going to stretch it to 15 centimeters. So the question is, how much potential energy, question mark. How much potential energy do we have? It will be 1/2 kx squared. You should have a good k from above. And the x now is not going to be 0.10, but it's going to be 0.15. And you can get a good value for your stored energy at 15 centimeters. And then finally, the last one in the series is question number 8. And on question 8, this is a little tricky. You're asked to figure out the work required to stretch the string from 10 to 15 centimeters. Now, if you wanted to get super clever about it, you could make a force distance graph, and we could look at our starting point of 10 centimeters and an ending point of 15 and calculate the area under the curve. But it's much simpler. I mean, it would work and you'd get a good value there, but it's much simpler to remember that the work done when you stretch that string is going to be related to the change in the energy that the string holds. This is the big idea, is that work is related to the change in energy. So did the energy change when we pulled the spring? Remember here initially we had 800 joules. Then we stretched it 15 centimeters and got some new number of joules. There you should see a change in energy between these two values.
But there might be,
whatever that change in energy is, that's the work that was done. Remember, change in energy is E final minus E initial. Okay, question 14 has to do with a vocabulary word that you're likely to see on the test. You will see it on the test. And that word is elastic and inelastic collisions. In an elastic collision, for example, a ball falls down, bounces, and if you really have an elastic collision, that ball comes all the way back to the same height that it started. In other words, there was no heat lost during the collision. No heat. Do elastic collisions really exist? No, they don't. There's no such thing as a really elastic collision, but some collisions are close to elastic collisions, like when two billiard balls hit. There's very little heat that's exchanged during that collision. So sometimes, for simplicity, we model a collision as being elastic, even though it isn't quite elastic, because there's always going to be some heat generated during the collision. An inelastic collision, on the other hand, is one that is the kind you're familiar with, where the ball bounces up to a lower position than it was before. In other words, there was some heat exchanged, some heat generated during the collision. And these collisions are called inelastic. So in an elastic collision, one of these, you don't have to worry about any heat being lost. Question 15 involves bowling ball, and your job is to figure out the work done in bringing it up 0.8 meters over some unknown number of meters and then down 1.4 meters. So let's see, and it goes up 0.8 meters because it started at 0.6 and it went to 1.4, so that must be 0.8 up. So we need to figure out the work on each leg of the trip. And the first leg, our force is just the same size as mg to lift it up. Our distance is 0.8, and the angle between the force vector and the distance vector are, those vectors are aligned, so there's no angle between them. And so it's cos of 0, and cos of 0 is 1. So that's for the first section, and to that we can add the work on the next section, which will be the mg again. M is 8. The distance is unknown, but it doesn't matter because the force is upward through this section, but the distance is sideways. Upward force, sideways distance. That's a 90-degree angle, and cos of 90 is 0. And then the last leg, we still have that exact same gravity force. This time the distance is 1.4 meters of travel. The force is still up. As you're lowering it, your hand is lifting still upward, but the distance is down. That's a 180-degree angle, and the cosine of 180 is -1. Add them all up, and you know your work that was done. Or if you're clever, you can just simply take the shortcut and just go straight down from a height of 0.6 to a height of 0, and because it doesn't matter how you get there. Remember, the work done is independent of the path, so may as well just go straight down, and it's the same amount of work. So you can abbreviate all of these steps very nicely by just doing mg, the force, times a distance of 0.6 meters below where it started, times a cosine of 180, which is -1. Because as you lowered it straight down, the force would be up, but the distance would be down. So either of these two should yield the exact same result. This value and this value should be equal. Okay, next question. Uh-oh, it's not. On question 16, you are asked to find this V at the top of the arc. And at the top of the arc, we've learned that that V is purely in the x direction. That will come in handy later. And the idea here is you want to look at the kind of energy that you have here at this initial moment, the kinds of energy you have here at this final moment, and using the principle of conservation of energy, set them equal to each other. That the initial energy must equal the final energy. The initial energy at the beginning, you've got no height. Height equals 0 to begin with. So your energy you have to start with is pure kinetic at the launching point. But at the top here, we've got two kinds of energy. We've got some kinetic still, because we're still moving forward, but also because we've got some height. We've got some potential energy of gravity as well. So there should be two terms here for the energy at this final point right here. Notice that every term has an m, so like usual, they'll cancel out. And then that only works, of course, if every term has an m. And then you can solve this equation for the final velocity because the height is given as 11 meters, so we know that. Solve for the final velocity, and then that final velocity gets used in part B because that final velocity was the x velocity, and the x velocity was always present. It never changes. We've learned that last semester. X velocity always the same. So this x velocity is part of a velocity triangle that was present at the beginning. We have Vx, we have a hypotenuse, and you should be able to get that unknown angle because that unknown angle is related to Vx and the hypotenuse by cosine. Cosine equals equals adjacent over hypotenuse. That would be Vx over 40. You will know Vx, you know 40, and then you can solve for the angle. On question 17, we've got a girl sliding down a slide, and we have the existence of heat, which we haven't dealt with too much. But the idea is still going to be the same, is that the initial energy will equal the final energy. Initially, we're at rest, presumably at the top of the slide, and all we have is gravity energy, mgh. So that's our initial energy. And then finally, the energy goes into two forms. There will be some kinetic at the bottom, some 1/2 mv squared, but also there will be some thermal energy. And in this problem, you have been given a value for the thermal energy, the heat, 300 joules. You know the mass, I believe, is given. Yes, it's a 25 kilogram girl, so that's given. The g, of course, is always known, and the height is given as well. And so you're just solving for the unknown of this velocity. On the next problem, 18, we've got a situation with a spring. The initial energy is purely potential when the spring is loaded back. So you know the formula for spring potential energy, I hope. The final energy is purely kinetic, and hopefully you know the full equation for that. So it's U spring, our initial energy, will equal the kinetic energy afterwards. The only thing we don't know in all of this equation is the x, the amount that the spring was stretched back. The mass requires a little bit of work because it's given to you in grams, right? It says 75 grams, but you know that there's 1,000 grams is equal to 1 kilogram. So that means the decimal has to shift by 3 places. All right, 1 kilogram, 1,000 grams. See, that decimal moved back 3 places to get the grams. Next question, one you'll see on the test, involves a bullet hitting a block attached to a spring. And the first thing we want to do is figure out the speed of the bullet block system immediately after impact. So we have to use conservation of momentum to deal with that collision because we can't deal with the heat directly. So Conservation of momentum, to start with, we have two separate objects. So we'll write the big idea, of course, is the initial momentum is equal to the final momentum. And our initial momentum is composed of the momentum of the bullet times the velocity of the bullet plus, did I say momentum of bullet? The mass of the bullet times the velocity of the bullet plus the mass of the block times the velocity of the block. And that should equal the final momentum, but finally the two are going to become one. We'll have the mass of the bullet and the mass of the block combined, one total mass for them, and they'll have some new velocity that they both share. If we think about the terms in this, the velocity of the block before the collision is 0 because it's not moving. So we just have one quantity on the left, mass of bullet, velocity of bullet, and we know it, and then we'll be solving for the velocity that they both have. In part B, you're trying to figure out how far the spring compresses. This is now a conservation of energy problem, and remember the guiding idea will be the initial energy equals the final energy. And initially we've got the block and the bullet traveling with kinetic energy. They'll have some speed after that collision. So our starting energy is pure kinetic. I hope you can see that. How much mass? Both. They're both moving together. Little m plus big M. And then the velocity that they'll have is the velocity that we just calculated, velocity of both squared. So that's our initial kinetic energy. And then as time goes by, we'll start losing kinetic energy and storing some energy in the spring. But at the moment of complete compression, the energy will be pure spring energy, 1/2 kx squared. So you'll need to carry your answer from part A into part B for V both. The K of the spring is given, so we know that, and the only thing we don't know in this equation is x. So here you'll solve for x. Solve for x. And in the last part, we're trying to figure out how much heat was generated in the collision. How much heat was there? Well, if we go back and think about energy now, we can look at our initial energy was pure kinetic. And by initial, I mean very initial, before the collision and anything. All we had was 1/2 little m times the velocity of the bullet squared. And that velocity was, what was that velocity? 140 meters per second. And that's our total energy to begin with. Our total energy to end with will be this spring energy plus some heat, E thermal. And so your job on this one is to solve for that thermal energy. We're trying to solve for this guy here. But we know everything else. We know the initial kinetic energy. We know the final spring energy. The missing energy, I'm not sure I said that right. We know the initial kinetic energy. We know the final spring energy. The missing energy must be this, the energy that went to the friction as it came to a stop. Okay, next question. Okay, we're on to our next page now. Last few problems. Question 1, simply calculate the kinetic energy, 1/2 mv squared. But you need to first get your kilometers per hour into meters per second. Don't forget, 1,000 meters equals 1 kilometer. In question 2, I try to trick you by giving you two kinetic energies and asking you to tell me the total kinetic, but I draw them with directions associated with them. But remember, kinetic energy is not a vector, no direction at all, just a number. Like if you have 25 cents in your left hand and you're lifting it upward, and 25 cents in your right hand and you're moving it sideways, you still only have 50 cents. You don't add your money like vectors, and you don't add energy like vectors either. So just add the two up and get a total. On question 3, you've got a coin with 5,000 joules of potential energy. Presumably, the law of conservation of energy is valid, so you can say that your initial energy, which is purely potential, will equal your final energy, which is purely kinetic. So that means the kinetic energy must also equal 5,000 joules. And our goal, though, is to figure out what the mass of the coin is. And since we know our speed is given as 400 meters per second, we know the speed check, we know the kinetic energy check, and we can figure out the mass. Okay. On this one, we're looking at, on question 4, we're looking at a spring that's been compressed, and we're going to shoot it off and try to figure out the speed just before it hits the ground. This is a classic conservation of energy problem. So we can equate the initial energy with the final energy. That's the guiding idea. But the initial energy is composed of two types of energy. You have to be able to see them both. There's some stored energy in the spring, some 1/2 kx squared. But there is also some gravity energy, stored gravity energy. So our initial energy comes in two forms, some kx, 1/2 kx squared, and some mgh. Finally, though, our height is equal to 0 just before we hit the ground. Our spring has been released, so we've got neither of these two types of energy exist anymore. The final energy will be pure kinetic, and it's your goal to figure out that velocity just before it hits. On question 5, you're bringing some object, a box, from a low spot to a high spot, and this problem is intended to remind you that for working against gravity, the path is not important. It's independent of path. You do just as much work going up and over as you do going sideways. We're not doing any work against friction because it said it was a frictionless thing. It's a gravity force. You could also go down and over and up and over and down and over and up and down and over. And no matter what path you choose, you do the same amount of work. So in other words, you get to choose the path you want to go. And the easiest path is this one because the work done here is equal to the force times the distance times the cosine of the angle in between. The force is just the gravity force. That's all you have to do to overcome its weight. The distance is the height that you go, which in our case is 8 meters. And then along this path, the gravity force and the distance are aligned, so the angle is 0 and cosine of 0 is 1. And of course there's no work done on this path because the force is upward, but the distance is sideways. That's a 90-degree angle, and cos of 90 is 0. So this is the easiest path to evaluate the work done against the gravity force. Question number, we are looking at a distance that a car can coast up the hill and just come to a perfect stop at the top. This is a conservation of energy problem also. The initial energy down at the bottom here is pure kinetic. The final energy at the top, if you do indeed coast to a stop, is pure potential of gravity. And you will go up a height h. And so the objective here is to first solve for the height h that you arrive at, and then once you know h, you can take advantage of this this triangle here, which I believe, let's see, it's a 10-degree triangle, and you can figure out the hypotenuse, which is d, given that you know the angle and you know the opposite side. On our last problem, we're trying to find the velocity of the bullet. To do that, we're going to first solve an energy problem to figure out what the velocity of the pendulum bullet system was as it was beginning its upswing. And so we can say that the energy initial is equal to the energy final. At the end, we've got all mgh. What's the m here? It's everything, because everything goes up. There's a little bullet still in here. At the beginning, we have, at the bottom of the swing, we've got all of the speed that the system has. So we've got pure kinetic. It's the same m. So kind of actually doesn't matter what the m is, as long as you recognize that it's the same m at the bottom as at the top. It cancels out. And you can solve for the v, and this represents, remember, the v of both bullet and pendulum together at the bottom of the swing. So we solve for v, and we'll keep that v in mind. Now, let's go back and look at the momentum part of the problem right here. And using momentum, we know that the initial momentum should equal the final momentum. Remember, we can't just go straight to energy here because there's an unknown amount of heat that's lost in that collision. So let's see. Initially, we had two objects. We had the mass of the bullet times the velocity of the bullet, and then we also had the mass of the pendulum times the velocity of the pendulum, which was 0. And then after they collided, we had the mass of the bullet plus the mass of the pendulum all together as one times a velocity that they both shared, and that velocity you know because you have solved for it just a moment ago when you figured out the energy. And now you're prepared to solve for the velocity of the bullet because you know everything else. So remember, energy, if we're working backwards in time, energy first, then the speed of the bullet, you have to use momentum. Momentum, energy. Here's a little clue. Had we been going the other direction, in other words, we know the speed of the bullet, and we're trying to figure out how high it goes, then you would solve for momentum first and then energy. So it depends what you know and what you want to know. Good luck on the test, everybody, tomorrow. And here's a little bonus for all you studious folks who watched the whole video. If you, on your test, write your whole middle name in addition to your first and last name, I'll give you a little bonus. But you have to promise not to tell the other students. Otherwise, I have to dilute the value of that bonus. Let's just keep it our secret.